it needs multiple of this series or like a series of talks. But today, actually, I need to talk about something recently happened, right? Like something um, um, maybe a few weeks old um, happened, and there is a lot of fuss about it, right? And there is a lot of, you can, if you Google latest James Webb findings, you're going to see a lot of, media coverage about latest findings, okay, recent research. And I didn't like it, actually, when I read all these articles and say, what, like it is, the media coverage is too bad. It's just basically trying to create a fuss about something that doesn't exist really. So, so today talk actually is going to be slightly, it's not technical. I don't want to, it's not a physics class, right? And also, like, I don't want to basically say, okay, it is beyond, oh, this is a good image, okay? So something in between, something is not that technical, okay? But also, like, it's not that, it's a good, a very nice, good images, okay? And so I'm gonna basically give slightly like a background before I basically go to the like maybe in the end of the talk. Actually, I'm gonna basically discuss this bad coverage actually about James Webb happening. Okay, like spreading very untrue statements about some of the latest findings. Okay, okay. So I'm gonna basically cover starting with why we need another IR space telescope, okay? And I just basically, as I mentioned, I'm gonna basically discuss very recent discoveries, okay, for James Webb Space Telescope. Okay, so let us basically, before with like when we talk about infrared spectrums, of course, like everyone familiar with the visible lights, okay, but we know this is actually our visible lights is electromagnetic waves, similar to the waves coming from Wi-Fi or like cell phones or like, but actually it has higher frequencies and somehow actually it's, our eyes actually can detect it. So, but this band actually is a very narrow band, okay? And by the way, actually, because the speed of light is constant, so we identify the spectrums also not by frequency, we identify by something called the wavelengths, which basically, like you can think about actually a wave, and between two high of a wave, like basically a sine wave, for example, actually goes up and downs and up again. Between two high or between two bottoms, actually, this is actually the distance, a physical distance, we call it a wavelength. So when we identify our visible lights, actually our visible lights is between 580 to 700 something, right? 700 nanometer, right? So that basically is the wavelength for our visible light, the light actually you see, actually your eyes actually detecting today. But if it is longer than the 0.8, okay, like 0.7 something, okay, that is basically, we call it infrared. And of course, like our eyes cannot detect that, right? And if it is between the 0.8 to like 3-4 microns, micrometer, okay, this is a near infrared. And if it is longer, between 3 and 15, and we call it basically the mid infrared. And it could basically go all the way to the millimeter wave, okay, to basically 100, like almost like a 900 micrometers. And this is, we call it ultra infrared, and or like sub-millimeter waves. And this is actually, by the way, actually is very important spectrum also for astronomy. But of course, like today, we're gonna only cover the James Webb, which James Webb, it is designed to look for between something like between the 0.7 all the way to 25 micrometer. So basically, all the way to 25 micrometers, that is basically the sweet spot for James Webb. There is some other older, very older space telescopes covering higher, longer than that. There's a very famous telescopes called Spitzer, decommissioned recently, not recently, like a few years ago, but that was also like an infrared telescope. But James Webb actually covered like sweet spot, as I mentioned. It is between the covering between reds all the way to 25 micrometer. So why we like infrared? Because infrared is a spectrum, okay, important spectrums for not hot subjects. Okay, like if there is any like planets, clouds, comets, it is dust clouds, colder stars. All those actually emitting in infrared. So typically, if you go with your own telescopes, okay, into the sky, if you want to see those, you're not going to basically be able to detect it with your visible light telescopes, correct? Or like visible light cameras. You need an infrared cameras to detect those. So most of I basically I think actually this is my statement is most of the next advances in science and astronomy will happen in infrared. Okay, on Earth we almost maximize the limitations with all these big, very large telescopes. Actually, like the 30-meter telescopes, the 40-meter telescopes. Like there is plenty of wealth of telescopes actually in the visible lights actually on Earth. So that's why basically, like if you want to see those very dark or like cooler subjects, you need to go basically infrared. But there is another thing actually, the far distance galaxies, they are way redshifted. Is anyone familiar with this term, redshift? Maybe I'll explain it later. I'll explain it later in a little bit more details, but means that is okay because it is the universe is expanding, and while the light actually from this distant galaxy arriving to us, it gets stretched. Okay, this means that is okay. Something in blue, all of a sudden, actually, it depends actually how far from us now. It basically stretch into the red, and this is we call it the redshift. And I'll talk. I'll explain this a little bit details later. So, if you want to do any advancements on those planets, early stars, evaluations, clouds, you need to go infrared. And also, like if you want to do highly redshift galaxies, actually, also like you have to do you have to use the infrared. And of course, like you're gonna see a lot of missions. There is, of course, like this is not the survey of all the missions. That is actually some samples of the missions, and you can see some of these missions is designed specifically for special spectrum. You cannot basically make a mission to cover the whole entire spectrum from ultraviolets all the way to infrared. So you typically design your mission or like your observatories actually to look for a specific spectrum. Okay, of course, like the visible light actually is most common one. Everyone has a telescope today, right? So, and as I mentioned, the Webb will be on the infrared spectrum. Okay, so if you want to build an infrared telescope, someone will basically, okay, I can basically take my telescope, I bought an infrared cameras, and I make an image. But it's not as that easy as we can see. There is 3 challenges, or like much more than that. But that is the main challenges actually for infrared astronomy. first actually is the absorptions profile of our atmosphere. So you can see, can you see my mouse when I move my mouse? Can you?
Yes.
Yes,
Okay,
we
good.
can.
Yeah. Okay, so that is basically, this is the wavelength in like horizontal axis here. This is the wavelength, like this is 5 micrometers, this is a 10 micrometer, 15 micrometers, 0.1. You can see like in ultraviolet, like remember, this is actually is our, the range for our visible light, right? From starting from blue, violet, actually all the way to red. So you can see like our atmosphere, it is somehow designed to not absorb the visible light to some degree, all right? So you can, that's why we can see the sun, we can see like in the night stars, all of them actually in this range, emitting in this range, and we have sun, correct? Like we wake up at the morning, actually we have sun, we can see everything around us. That's very good, okay? But in ultraviolet, actually our atmosphere sense, okay, to nature, actually, it is ultraviolet is very harmful, and somehow we are protected from that. When it comes to infrareds, also it is big absorbed. You notice actually between 1 to 10 micron, it is basically, it's almost blocked, the infrared spectrum. So it's very hard to make a telescope on Earth on this range to basically observe an infrared emissions coming from distant stars or coming from infrared emitters. Okay, but amazingly, there is also like another opening in our atmosphere for the 10 microns. Okay, and this is very interesting one, right? And literally all our heat around us actually emitting in this range. This means that is there is that our atmosphere actually, or our Earth, it has very interesting balance between the incoming energies coming from the sun and the escaped energy, and there is very interesting balance, okay, between this incidents actually of energy coming from the sun and the emitted energy, escaping energy. Otherwise, actually, this global thermal runaway could happen, and this happened actually in this range around the 10 microns. And by the way, actually, the CO2 actually play a very important role actually in that, because actually CO2, if we don't have a CO2 in the Earth actually the Earth will freeze pretty much. So we need a little bit of CO2 to keep the Earth warm, like the warmth actually we have, but too much CO2 actually we will get like this thermal runaway. Back to the subject, you can see basically like in our range of interest, there is, if you want to make a telescope, actually in 10 microns, I think actually you can basically make it from Earth. But there is another problem, I'm going to talk about it next. Another problem actually is what is called the thermal infrared. What does this mean? Means that is okay, everything, me, you, the computers, the walls around us, the Earth itself, the trees, everything actually glow in the 10 micron range. So there is everything around you is basically glowing. That is equivalent. You take your telescope and try to make an image during the day. Anyone can do that? No, there's no way you can do that, correct? Why we cannot do that? Because actually we have during the day what's called the Rayleigh scattered, okay, which basically cause the light coming from the sun to be scattered, okay, in the bluish, okay, and that's why we see the sky blue during the day. But this Rayleigh scattered actually almost goes to zero, or like almost actually goes away at the 1 micron and the infrared. But this thermal radiations, as I mentioned, this is thermal radiations. All of us actually, everything around us actually irradiate at the 10 micron 10 micron range. So pretty much actually, if you have a 10 micron camera on Earth, okay, what you're gonna see, you're gonna see basically everything around you is glowing. Somehow, okay, like you can buy, by the way, actually, like those cheap infrared cameras, you can buy it for like few $100s. Those actually in very near infrared. This is almost like a visible light once, but they remove the filters on top of them, okay, and they basically can take around like 1 microns. And if you want to buy like a 10 micron camera today, I think it should cost you a few hundred, maybe tens of $1,000s. It used to be like $150,000 and stuff like that, and very low resolutions. But the quality, like you can basically Google thermal images. You can see the quality is terrible, right? Because the resolutions and the depths of each pixels is terrible, correct? Because there is not the what's called the signal to noise ratio is very bad, right? Just if maybe actually after the talk, you can Google thermal cameras. There is people selling this stuff, correct? But you cannot get the details out of a thermal camera today, right? Why is that? Because that's basically everything around us, as I mentioned, everything is around us is glowing. The sensor, actually, the camera itself actually glowing, actually, it's like almost like a light bulb. The sensor itself actually will be glowing at this range, okay? Like good, actually, we don't see infrared, otherwise, like everything actually around us actually will be glowing, as basically there is a light bulbs, right? So this is another problem actually in infrared. Another problem actually with the infrared astronomy is the sensors itself. And maybe actually I can give some more information, a little bit more information later, okay, about that. So as I mentioned, actually, if you want to do the around 10 micron, I want to take an image in this range, in this cool image, actually around 10 micron, the sensor itself is glowing. There is a lot of, means that is okay, there is a lot of noise, photons coming out of the sensor material itself. So the only way actually to cool this, you have to cool this down, and you need to cool it into a very, very cold temperatures. You have to cool it all the way to 4 kelvins. In matter of fact, actually, you have to cool the whole entire telescope. You have to cool, actually, if you want to do a good 10 microns actually from Earth, you have to cool the whole entire Earth, which basically is not going to happen. Okay, you cannot get reasonable. But if you can see, like it is about signal and a noise. If your signal much higher than the noise floor, I think actually can make an image, right? But for these faint subjects, we need to try to resolve. I think actually we have to be way far away from Earth. And we'll see that later. So that is basically a very interesting. We have to call the sensors of this infrared to basically get reasonable images. Another thing actually, like challenges with the infrared astronomy is this, with the sensor itself, is what's called the materials. Like for example, here actually we're using in your iPhone, for example, okay, using the CMOS sensors, but that actually like the silicon is a material does not get excited enough to generate photons using infrareds. So you have to use a very exotic materials to create those sensors. Okay, so let us solve the first problem. Okay, like we said, okay, we need to be away from Earth, okay, to make a good infrared. So what there is one spot. If you want to be away in a quiet place, actually, and a reasonable place, there is many reasons actually why you have to go to this spot. There is something called Lagrange 2 point, right? That is actually almost like a 1.5 million kilometers away, or like 1 million mile, around 1 million mile away from Earth. Okay, and that's basically, it's a point outside after the moon, correct? What is Hubble? Hubble actually is orbiting around Earth, like a Hubble Space Telescope is orbiting around Earth, but James Webb has to be way far from Earth, okay, in this Lagrangian point too. What's so special about this point, or this orbit, is it is a stable orbit or semi-stable orbit, means that is okay. If you put an orbit in these locations, somehow actually will follow the Earth. So you always your mission or a telescope will be always follow Earth, okay, and you don't have to spend so much energy or like so much fuel to keep this telescope in these locations. Okay, it just basically orbit. It's far enough so we don't get thermal radiation from Earth, and also like it is a stable, semi-stable point. It can it follows the Earth. Like when the Earth rotates around the sun, actually this point actually also rotate. Okay, I don't want to basically go to this dynamics and stuff like that, but actually like that is basically is the idea. Okay, so that basically is the structures of James Webb Space Telescope. And you can see if this is the sun, of course, like here actually will be Earth. Okay, like it is far away from the other side of sun all the time. And we have a big shield. Okay, like this is almost like a tennis court size shield, right? And why this shield is about is basically try to basically protect all these optical components from the sun radiations. Okay, and you can see like, oh, yes.
Can I ask a question?
Sure, absolutely.
Yeah, sorry. Is the L2 point is the James Webb actually in the shadow of Earth, or just far away? Is that
no? Actually, yeah, it's just basically it is in the shadow of. Actually, this is very good questions. It is in the shadow of shadow of Earth, but of course, like you need a sun, because actually you need the what's called you need the like electricity to power this telescope. So you cannot basically be in the shadow of the sun of the Earth. So what you're gonna do, that is basically why it is circle. You have basically go up and down in a circle. You are in this spot. That's why we call it semi-stable. You are in L. If you are exactly in L2, you will be in the shadow of the Earth, and you're not gonna get enough sun to power your telescope. So you have to basically do a very interesting orbits. Actually, you have to go up and down. You can see like this circle. So it's not only like in one spot and going now. Actually, has a very big rotations actually around L2.
Oh, okay. Thank you.
Yeah, that the orbit of the telescope around the L2 point is comparable in size to the orbit of the moon around the Earth. So it's big. It's not little.
Correct. Yeah.
Okay. And then for cooling, do you need to also add the helium component, or is the space itself cool enough?
So that's basically is a good thing. Okay, so of course, like to cool the whole entire thing actually is not practical, correct? So what they did actually, when they did this sun shield, 5 layers of sun shield, and this like reflecting materials, and it's basically it cooled down. Like you notice actually from this side, it's it's almost 300 kelvins. The other side actually it goes. The whole telescope will be around in the range of 40 Kelvin. That's very cool. And this enough to do near infrared imaging, like up to the 5 micron. That is basically enough for a 5 micron imaging. So what about the 10 microns imaging, or like mid infrared images? They have to cool the sensor, as I mentioned. So this is actually have to be not passively cooled. It has to be actively cooled. And this means that, okay, they have to use helium, liquid helium, to cool the sensors. So they have a tank inside the spacecraft itself, and very complex systems. Actually, of course, like I don't have time to cover it. It's very interesting stuff. But there is a pipes actually coming from this spacecraft all the way through the sun shields, and to basically cool down the sensor of the or like basically we call it MIRI, like mid-infrared imager. So the MIRI actually today, as we talk, actually they call it down to 6.5, which basically was the science team actually said, okay, this is good enough for us. We don't have to push it actually lower than that. That's basically was good enough. Most of the images you're gonna see from MIRI actually is perfectly fine with 6.5. And in matter of fact, actually, one of the lifetime of the telescopes, it is based on this helium containers, actually, how long actually you can survive. And yeah.
Thank you.
Okay, so as I mentioned, actually, that is basically it's solar powered, and this is the shape of the sun shield. Okay, all the controls actually in this in this in one side. The other side actually it is the what's called the observer file, all the optical components actually in this side. So how big actually compared to Hubble Space Telescope actually? So this is actually 6 meter, and you notice actually it says hexagonal, and Hubble is a classic round mirror. Of course, like this hexagonal shapes, because actually they have to fold, like they cannot. This is actually 6.5 meter end to end. Of course, like there's no big rockets can put this big mirror, so they have basically to segment it, and it has to be folded. And there is a very interesting, nice videos actually on the net to show basically how this actually get unfolded. So I encourage you guys actually to go and Google it and watch this those deployment, as you call it, James Webb deployment videos. It's amazing videos actually to watch. Okay. So what is the 4 main tasks actually for our objective of James Webb? So looking for the early, like, because there's so many questions about the early universe, and I'm gonna basically talk slightly more about that now, okay? And also, like, basically, like the shape of the shape of the galaxy. There's so many also like questions need to be answered about that, and how the stars actually get formed, and also like the exoplanets. So that is basically the main science team, okay, for James Webb. You're gonna see most of the publications coming from James Webb covering those 4 subjects. Of course, like people are very inventive. They can comment also different subjects like asteroids or like our planets and our solar system, like our solar systems. And of course, like this is, but this is the main theme of James Webb Space Telescope. Okay. So how this basically gets, I want to basically discuss actually the images we are seeing, like for example, the first image, okay? How did we do it, right? So of course, like this is the focal, we call it the focal plane. Like in the scope has a focal plane, we put our sensors on it. And this is actually where is the near cam actually, like you can see there is four main instruments on that, or like a 5 main instruments on the Hubble, on the James Webb, JWST. One of them actually is the near cam, which from the name, it is designed for the near infrared, near infrared, means that is up to 5 micro. Okay. And we have what's another camera is called MIRI, which will cover, but we cover the up to like from 5 to 27 micrometer. And we have 2 spectrometers. One actually we call it near spec and near cis. Okay. And we have also another camera, we call it for fine guiding systems. This is actually is a camera, but actually it is in the optical, mainly in the optical, and it is designed, it has, of course, like it has optical and infrared, and but actually it's designed to basically, because these telescopes actually should basically looked into a subject while it is moving, but it has to basically orient itself very precisely in the subjects for very long exposures. And actually, this actually it's amazing. Actually, they were able to use these fine-guided systems to track objects for very long time, like in theory, actually for like weeks. Actually, same subject, even actually the telescope doing two. Remember, actually, it's rotating around the Earth. Okay, not around the, like I mean, in with the Earth. Okay, also like rotating around in L2 itself. It has its own orbits, but it is so precise. There's a whole thing actually can be basically precise to point for weeks actually into single object. But let us basically focus on, we're gonna basically skip all those stuff. Okay, maybe this is some other talks. Let us focus on the near cam. So you can see that the near cam, actually they have two cameras, okay, because this is very important. Anything has, because the whole entire telescope is about this camera. So of course you have to have a redundancies. You have two cameras, identical cameras. And you can see that is okay, it has big square and four small squares. What does this mean? This means in this focal plane, I can take my image and I split it into two separate baths. And one bath has a big, one sensor, very big sensor, okay? And another bath has four small CCDs, or not CCDs, like CCDs, yes. Okay, we can call them CCDs, okay? So why is that? Let me explain. Why we have to do that? If you look into your iPhone, for example, okay? iPhone cameras, they call it actually, say, for example, 12 meg camera. Right? And what is the resolutions of this iPhones? Okay, it is, I think actually the latest phone is 1100 by 2500. That is basically the resolutions of iPhone 14, one of the cameras, correct? And in order to capture a photons for a specific wavelengths, your pixel has to be longer, at least double the size of the wavelengths of this photons. So for example, actually, if I have in the a red photo, a red color, or like a red beam, what is the wavelength of this beam? Will be 760 micron, 760 nano, which basically 0.7 micron. Okay, so what is the minimum pixel size actually should be? Will have to be double this number, okay? And it has to be 1 micron, 1.5 micron by 1.5 micron. Most of the cell phone images, okay, sensors, or like most of the cell phones cameras, the pixels actually it is in this range. It is 2 microns, around the 2 micron by 2 micron each pixel, correct? In order, because why you have to do that? Because we have to be larger than the largest wavelengths, which basically in this case, in our case, our cell phone cameras, it has to be larger than the 0.7. Of course, like something like you can find like a Samsung, for example, new phones, it can say, okay, it can claim that is okay, I can make 120 microns of 120 meg cameras. Of course, how do you do that? They make the pixels way too smaller. I think actually the limit today, it is 1 micron by 1 micron. There is some talks about even dropping that. But when you do that, actually, the images become very, very noisy. Okay. So let us back to James Webb. If I want to do a 5 micron, imaging, so the pixel size will have to be what? 10 micron by 10 micron. right? Because it has to be bigger, larger, at least double the wavelength of the spectrum I'm interested actually to take an image for. So when you do that, okay, imagine actually like a scenario that is okay. You want to design a CMOS CCD sensor, okay, for mid infrared, okay, or near infrared. So your pixel size is 20 micron, and you want to basically do 1 meg. Like the sensor itself is start to become larger, right? So that's why basically they have two sensors, one for the 5 micron, okay, and another one from near infrared until 2.5 micron, okay, and that's basically is this. So pretty much actually for this near cam, they have two imager or two CCD. One basically cover this one will cover the 2.5 micron to 2.5 micron, and those actually covering from up to 2.5 micron. Okay. Each sensor of those actually is the same resolution as this, but because actually like the wavelength is smaller, I can fit 4 in the same size. Actually, I'm fitting 1 image as a 5 micron range. Makes sense? Okay. So this means that is okay. I can have to take my image, I split it into half. Half of it actually goes to this sensors. The other half actually goes to the other sensor. Not by half, like physically, it is the same. Like I just basically the same image. Sorry. The same image, okay, goes to both sensors at the same time, pretty much. Okay, and this is basically how it looks like. And if you look into the what's called the near cam, it looks something like that, right? It just, you get your image, okay, and you're gonna basically have a beam splitter, okay. One split it into the long wavelengths, okay, and this is a short wavelength. A short wavelength actually means that is okay. It is as I mentioned, like the red to 2.5 microns. Actually, it goes this pass, and the longer actually it goes directly in here. Of course, like I have to have like any camera, or like you need to have you know, when you have your cameras, okay, like SLR, no one basically carry SLR in these days, but you used to have like of course, like I have to have your lenses and you have filters, and that is exactly what's happening here. Actually, this is actually a filter wheels, okay, and I'm gonna basically discuss why we need these filter wheels. One filter wheel for the long, for the short, and one filter wheels for the long. Okay, and this is simply our focal plane, or like this is your sensor housing, pretty much. So this is pretty much actually the near cam. Okay, and you can see that's actually is it has I'm not gonna go through the details of this, but it's just basically you can think about it. Actually, each one of those, actually each bus has its own wheel. It has multiple filters, okay, at different wavelengths, okay, and also like it has a pupils actually, like the opening. It can be a clear, or like it can has some other functionalities. Of course, like I'm not gonna, if you have a questions I can answer, but there is a lot of details actually behind this stuff. And this is how it looks like, right? Like this is actually how this camera looks like. Okay, good. So let's talk a little bit actually. So now we understand what is the challenges for infrared imaging or astronomy, and why we have to go to space, why we have to cool those sensors. So how is the camera looks like? So let us use the camera to do something interesting. So This is basically as a Hubble images. So by the way, actually, like very easy to differentiate between Hubble images and James Webb images. And the way to do it, you look into the diffraction limits, like you look into basically these bright stars, and you see here actually it looks like a cross, right? When you see this cross, you know exactly this is a Hubble image, right? Every telescope has in like point spread functions has a specific shape, right? And we can, from this point spread functions, we can identify the telescopes, okay? Pretty much, right? So when we look into this image, we know right away, actually, this is Hubble image because we see the cross. But when you see James Webb, when we see it later, it's gonna see like it is not cross. It is basically, it has 6, and I can basically talk if I have a questions why that happened. But yeah, if you have these questions, I can answer later. Okay, so this is actually it's very interesting Hubble images. Okay, and it has been done actually a long time ago, and never been done again. And why is that? To get this image, they call it Hubble ultra deep field images. To take these images, it took Hubble 21 days, one image. So imagine basically there is so many so many astronomers all over the world. They are lining to basically to book times on Hubble. Imagine basically like you say, someone would say, I need to do another Hubble ultra deep field images for another point in the sky. Of course, no one will give you the Hubble for 21 days for another single image. So people basically was begging about that for a long time, and basically they allow them to use Hubble for these images. But after that, Hubble has to be used, has to move forward. And why is that? Because this is actually a very faint subjects, and for Hubble to take these images, it has to point to collect enough light from the subjects to a degree that is okay, it can basically reproduce these images. Okay? And Hubble has a problem, okay, because actually remember, Hubble orbits Earth, right? So Hubble actually have one orbit around Earth actually in 1.5 hours, right? It's 90 minutes around. And not this the whole 90 minutes actually can do observations. At one point, it has to shut down, like they have basically close the shutter, close the telescope. So basically to protect it from light, either straight light coming from sun, or like it depends on where you are, or basically coming from the Earth itself. So basically, that means that is okay. You have only like 60 every 1.5 hours. Okay, you can basically take on exposures, and basically every 60 like make an image for 45 minutes and shut it down for 5 minutes, and you keep doing that again. Okay, and you have to do this days and night for 21 days to make this image. But when this image come up, actually it was mind-blowing pretty much. Okay, and of course, like they have to fix, not to fix, they have to upgrade Hubble 3 times to basically to obtain this. They have to basically upgrade Hubble with infrared capabilities, and they add infrared capability. Once they add infrared capabilities, they can go and look into the darkest area in the sky and basically try to obtain these images. And very interesting, actually, this image, except of course like a few like this big like this something with a cross, actually this is a local star, something in our Milky Way, very near stars, but anything else actually is a galaxies. So every faint spot actually in this is a galaxy by its mean, hundreds of billions of stars. Okay. So let us talk about actually a little bit how the story of our universe And we understand actually everything actually starts with a big bang or like inflations. Okay, but I think actually no one talk about big bang anymore. Talk about inflation most of the times, and everything was so energetic, then it cool off, and until it become like a 3,000 degrees. Okay, then after that it became the light disappeared from the whole entire universe, and everything actually become dark. Okay. Then magically, after a few 100 million years, light start to show up actually in the universe. Okay, and then basically the first galaxy start, or like the first stars started to show up actually in the in universe. Then it keep basically it take its shapes until today. So the local, like the close by galaxies, we know it's very well because we can observe it. Okay, but Hubble basically can go all the way to around 7-8 redshift. Okay, when you say redshift, means that it's okay. The wavelength it is stretched by this factor. If I say like for example, a redshift of 1 means that is okay. It is the redshift actually of the subject. It doubled. So a redshift of 1 indicates that is okay. This galaxy, it is 7 billion years away from us. So I can basically use this redshift to, if we can identify the spectrum of this galaxy, and I see where it is shifted, pretty much actually I can identify the edge, how far it is from. But it is not as simple as that. I explain why. Okay. So this also like a Hubble image. Okay. Or a Hubble, like this is very old slides. I got it from the web, and for Hubble, and you can see that basically any galaxy, okay, has a spectrum. Okay, what does a spectrum mean? Spectrum means that is okay at each wavelength. What is the emissions coming from it? Like how much light coming from it? So this is basically what spectrums mean. So in here, actually, this is a wavelength, and this is a spectrum of a galaxy. So this is a galaxy, okay, at redshift actually of 3, right? And you can see it is almost all it can like all the filters in Hubble can see this galaxy. But once actually you go deeper, like farther away, what will happen? Some of this filter, like some of the images, because actually the whole entire galaxy, it is shifted to the red. What will happen? Some of the filters actually, or some of the filter, if you put these filters in front of the camera, the camera cannot see this object. It can only see it in specific filters. Okay, like the more into the reds. Until pretty much actually Hubble will almost, it is goes beyond Hubble capabilities. That's why James Webb is basically very important, because like Hubble has a capabilities, it can basically get us into so far, because Hubble has its cameras can go up to 2 micron. James Webb can go to 25 micron. So basically, if anything actually get shifted into the 2 micron, beyond the 2 microns, Hubble cannot see it. It just basically see dark spot in the locations. In order to see this subject, what you need to do, you need to go to James Webb. That's what James Webb actually will be very critical to extend what is to build on what Hubble legacy is. Okay, so in order to, that is basically very important. Okay, in order to identify how far these galaxies are, okay, we have to basically look into, take an image, multiple image with multiple filters, and we see where is the image is disappeared, and based on that we can identify the what's called the age of the galaxy. But you can see there is limitations on Hubble, And that's why James Webb is go beyond Hubble capability. Okay, so this is actually the first image. So let us basically talk about it a little bit, okay? Again, so like first actually see like how basically the point spread functions of James Webb. It looks like it has 6, 1, 2, 3, 4, 5, 6, and it has some strides here, but okay. So we know for sure this is actually coming from James Webb because it is not a cross, not like Hubble. But how many basically hours required to make this image? This image actually they were able to create it in less than 12 hours. Compare that to Hubble, it took 21 days to get similar image. It's like it's mind-blowing, correct? Instead of 21 days, you're gonna get it in you can get this actually in 12 hours only. All what you need is 12 hours to get similar ultra deep field images, but actually you can get it much quicker. Okay, so it is basically like this. The image actually was like if you notice actually the sensors actually of James Webb, how many arc minutes? It is around like 2.5 arc minutes by 2.5 arc minutes, something like in this range. If you know that is because the moon is basically 30 by 30, correct? So it's almost like this image. Actually, we are looking into a spot in the sky. It is literally as a grain of sand, right? Like it is 2 arc minute by 2 arc minute. So basically, if you put a piece of sand in your fingers, actually extended like this, that is basically how much actually of the sky actually we are looking at in this image. And this image alone has like something like more than 5,000 galaxies by itself, just basically this image. And as you can see, some of them actually are what we are looking for. We are looking for the most reddish and fainted subject in this, and basically this could be a potential distant galaxy. Of course, in infrared there is no notation of color, right? There is no such color as like our eye identify colors because we are equipped to identify colors. But in infrared there is no notation. There is no such thing as called red actually in infrared. But what we can do is basically because actually we are having these filters in the infrared, we can say, okay, longer wavelengths, we call it red, shorter wavelengths, we call it blue. Okay, so in here actually, like in this specific image, they are using 6 filters. Remember, actually, I show you that is those filters actually in front of the cameras, and they use 6 filters, okay? And they can use the output from each of this filter, okay, to basically make this color. So this is a false color. Like there is no such thing, correct? Like this is a colored through computing. And this also like another same image, okay? But also like it is in the right hand side, which is this side, it is from using NIRCam, and in the left hand side actually is using MIRI, which basically is the mid infrared. And it's the same image, correct? Like the same image. One is like the same subject, everything, correct? And you can see there is something actually like this is actually the power. Why actually is the power of different spectrums? There is some stuff in the mid infrared cannot basically is not even. There is some details, and maybe actually later actually I have some other images. Actually, it shows that is basically like there is something actually in the. Of course, like both of them is not invisible. Like you cannot see the stuff actually in the visible. You have to see it actually only in the infrared. But even actually some of the stuff actually you have to see it in mid infrared. Okay. I'm gonna basically be a little bit technical for 2 slides. That's it. Okay, I promise. So this basically is a very recent findings. This is actually a very recent findings from James Webb. This I get cut and paste from recent article, or like not article, was a published paper, and somehow the media took this paper, and I read it. I read the news from the media, correct, like Facebook and YouTube's and stuff like that. Then basically I said, okay, well, why not actually I go and read the paper itself? So I just basically go and I read it, and I cut and paste actually this, and that's basically, you can see here. You remember actually in Hubble we have different filters, and based on where is the cutoff, like for example, actually this subject, okay, like the first one on the top here, right? It is in this filter, actually it showed up. In this filter it showed up, and at one point it disappeared. At that 0.8 micron, it disappeared. Okay, so we know that is this subject, the cutoff, okay, it is between these two filters, right? Between the 0.8 micron and 1.15 microns. So they identify 6 of those subjects, okay? And you can see, like, you know, every subject, it depends where far it is. And I can basically calculate, okay, what is the redshift actually for it. And based on the redshift, I can basically see how far it is, this galaxy. See, so for example, this is way redshifted, okay? I can see, like, it is blocked actually. It is basically between 4 microns and, like this, for example, this, the force from the top here, this one, it disappears almost in here, correct? Before the 2 microns and the 2.7 and the 2 micron, correct? Like in here. So this is for sure, this is actually farther away from this galaxy. And I can identify that, correct? Okay. I apologize. Actually, this is a little bit technical, but actually, I'll go through it quickly, correct? Okay. Also, like this, I cut and paste from the same paper. Okay. And what happened here, right? Let me actually, before I explain this, let me go to this this image, correct? You know, you notice actually this is supposed to be a continuous spectrum coming from galaxies, correct? Because galaxies has so many subjects, like it's supposed to have so much spectrums in most of the, like each galaxy depends on, it has a lot of all type of stars. So I can basically have a very continuous spectrum, but you can notice actually there is a break in the spectrum. There's a cliff in the spectrum. Okay. What's this spectrum actually? Why actually we have this break in the spectrum? By the way, actually we call this cliff is Lyman break. Like you can hear this Lyman break, Lyman galaxy. Like you're gonna hear this terms all the times actually in the web, or like like some scientific talks and stuff like that. Lyman break. What's this mean? Means that is okay. In the early galaxies, the light starts to shine, the first lights, correct? But remember, the whole entire universe was full of hydrogen, okay? And hydrogens, okay, will absorb absorb at specific wavelengths, correct? One of them actually is a Lyman, okay, and the second is called Balmer break, Balmer layers, right? So we know that is basically supposed to be, this break supposed to be in ultraviolet, deep ultraviolet, in the 100 nano, 0.1 micron. Yeah, 0.1 micron. Okay. But somehow actually it is this galaxy, we see this break at the 1 micron. This is from Hubble, correct? So that is basically what's called the like a lemon break, right? And this is how we observe the galaxies, and based on this break, where it is, the spectrums, we can identify what is the shift. Okay, let's go back to this slide. So you can notice actually those, like, remember the 6 galaxies from the previous image. So this is the spectrum for them. Okay, 1, 2, 3, 4, 5, 6. Okay, and each point here is basically coming from a specific filter, correct? Like we have 1.2 micro, like 1.2, the 1.5, the 2 micron, the 3, like, you know what I mean? It is basically almost like you're sampling the spectrum, right? And you keep doing that. So there is, you can see that basically this is the break, okay? Like this is like Balmer break, okay? Or like Lyman breaks, okay? Like for all these galaxies, okay? And you can see there's some galaxy, if you can see basically, for example, this galaxy, the Lyman break actually happened later, you know, that is actually, this is an older galaxy than, for example, this galaxy, okay? And you can have a models, and you fit these models, and what you basically, you can have a model, and you say, okay, what is the model it fits this galaxy, okay? And you can see that is, okay, those galaxies, okay, this is the models perfectly fit these points. Okay, you have your points from your observations, okay? And you can basically have a model on how the galaxy actually gets generated. And you say, okay, I'm gonna perfectly fit this, I could perfectly fit that, okay? And what will happen, something interesting happen, they discover that is, okay, those galaxies is as big as our Milky Way. So it has mass, okay, as big as Milky Way, which basically our Milky Way, it took 13.7 billion years, correct, to become the Milky Way we live in today. Because actually the model we have, okay, on how this big globe, like all this gas collapse in a way to generate galaxies, okay, the galaxies we know today, like for example the Milky Way with all this you know, arms and the shapes of the galaxies. There is so many perfect models and theories about how our galaxy get formed, and it takes actually to get this amount of light from Milky Way, you need 13.7 billion years. And those galaxies, it is only 3 to 400 million years after the Big Bang. So that is something definitely a surprise to everyone in the science community, because I say, how this actually could possibly happen, correct? Our theories, okay, or every single theory we have, okay, says that is, okay, to achieve this mass from stars, okay, or like all these stars actually to produce these lights, you need this much time, okay? It slowly cool down, stars start to form in the galaxies and take its shapes. But what we notice here, based on this informations, okay, is galaxies actually are in the early universe basically have the same lights, actually same amount of lights actually as our galaxies, okay, current galaxies, which basically this is a big puzzle. And you can see, if you go and search on the web, actually latest finding in the web, you're gonna basically get those articles like that, which basically I really hate it. That's why I make these slides to clarify it for you guys. Okay, people say, oh, like this is actually all our theory about the Big Bang is wrong. There is galaxies actually as old as the universe. Actually, how possible actually you can have a galaxy as older than the universe itself, stuff like that, correct? So, but really, actually, this is not what is like the discovery actually saying. It's saying that is, okay, we, based on our finding, this is the new data points. This means that it's okay. We need just all what we need. It's not about like the Big Bang actually like the Big Bang is wrong or something like that. It's not actually. It is all what it says. That is okay. We have a new observation, new data points. We need to slightly modify our theory on how our galaxies evolve, and how because it could be basically the early universe is slightly different than because the best model describe our universe today is called lambda CDM. Okay, what does this mean? It is based on what's called dark matter. It means that is okay. The people say, okay, we have all these hydrogens after the Big Bang filling the whole entire universe. The whole entire universe is filled with hydrogens, and we have what's called dark matter. It basically some of the hydrogens actually to collapse and make galaxies, and lambda coming from this actually the expansions of the universe. So all this actually is a very established, very well established science, right? It means that is okay. This is a new data point, okay, because we don't know those galaxies. Okay, is not as big. It is very clear they are smaller, irregular shapes. This means that the stars actually formed beside each other's, close to each other's. That is completely different dynamics than what in our galaxies today. So basically, like if you try to model the current galaxies and the early galaxies, maybe they are different. So it is very early to come out with articles that says everything is wrong, everything is broken, and we cannot basically like a new science has to be written. Extremely early. It just basically even actually the guys actually in the articles it's saying that is okay. All what they say, okay, we have only few in the whole entire spectrum. We have only few points in the spectrum. So what we need to do, we have to revisit those galaxies again, and instead of actually using images, we can basically use spectrums and have a very detailed spectrums, okay, for those galaxies, and we can basically confirm, did you really actually have a new something new? I don't think actually it is. I'm gonna give my humble opinion. It's not about everything is wrong. No, actually, it basically means that it's okay. We need to tweak our models to produce these galaxies. All that mean, okay, because the current model actually cannot produce those galaxies anymore. But before we conclude that, we have to go and do more accurate spectrums of those galaxies before basically we jump into this type of conclusions. I'm not sure actually what happened. Yeah, you can see, for example, it's the same image, okay, which we can do basically. You can do spectrums, okay, and we can like this, like for example, actually here actually it shows that is okay. This is Einstein rings, okay, and you can see that is because there's gravitational lensing and those objects are the same, and that is basically the capability. Oh, sorry, actually, this is the capability of James Webb. Actually, can do not only do imaging, this nice image, but it's also like can do spectrums. Like you can see, like one image is here. Actually, can do a lot of spectrum for it. Okay, but those actually, yeah, can do spectrums as well as an image, because you can like you can come out actually with very interesting science actually using only like the spectrums. I think actually I'm gonna I'm past my time, so I'm gonna stop and we can go for Q&A.
So the web has actually made us, instead of answering a lot of questions, they've just created a lot more.
Actually, much more. I covered only one image, by the way. This is the first image. There is a lot of like there is every image actually they produce. Typically, it comes from the science. Like those images goes to science teams, and every image it takes, or every spectrum takes, it goes to the science teams, requested it, and of course, like it is directly become a paper or like a scientific findings. So yeah, it is actually. So, and this is expected. Each time we point a telescope into the sky with a new capability, we discover something new. When Galileo basically look into the Jupiter moons, actually it changed everything. When Hubble looked into the sky 100 years ago, only 100 years ago, we basically assume we have only one galaxy. Like when Hubble looked into its new capability, big, like uh, uh, a larger telescopes, we discover that is okay. There's like it is not only one galaxy. Matter of fact, there's multiple galaxies. Like in the human life, only 100 years ago, we assume that is okay. It's only one galaxy, and it is always like that. Anytime we look into the sky with a new capability, there is a new discoveries, a new questions. Actually, it's historically this was the case.
That's amazing.
Salem, is the spectroscopy done here on Earth, or is it done on the web itself?
No, actually, so the spectrum basically like it has a spectroscopy actually happen in on James Webb. The data, of course, get analyzed. So basically like it depends actually, because like every instrument has its own has its own capabilities. Typically, they use grisms, okay, which are prism and like a grading, and it goes basically to a CCD and takes this image, and this raw image actually it gets shipped into its surveillance. So how the resolution of the spectrogram actually depends actually how much of spectrum you can spread it on over your CCD. Okay, that is basically easy resolutions. So some of them actually don't need so much resolution, so you want to basically do survey. So there is a near CIS. Okay, it basically can do surveys, and there is another spectrum. Basically, like if you want to have a precise and very high resolutions, of course, like you have to basically, in Earth, actually, when you do spectrograms here in big telescopes, actually, they get a blade, or it used to be at least, they get a blade and basically make a hole for the object. Actually, you need to take a spectrogram for it. Like you get a metal plate and basically make a hole. You know what is your fields, and you go and design actually a metal hole. So basically, only like you make a spectrum for, so you don't get a light pollutions from the surrounding. And something similar actually happened in James Webb. But actually, of course, it has to be electronically. So they have like almost like an electronic shutter. With this is something completely like 1,000 by thousands pixels shutters actually open and close in front of in top of each pixels. So it can basically use to isolate specific object and basically take a spectrum for it, or multiple objects. Like it depends actually what in the field actually you want to analyze. So basically, like the raw data actually happen on the craft and or on the telescope, but actually the data get analyzed, raw data get analyzed, because remember there is no compute power actually in it's just basically a controller. It just basically turns this off, turns this on. This is heated. Let us basically, like, it's basically management. The CPU on this thing actually is not like it's a very old processor, basically Power PC, like 20 years old, maybe much maybe actually older than 20 years old CPU. Yeah, it's like some form of Power PC. Because remember, actually, this is only a controller. It does not need the latest and greatest Pentium 7, whatever, blah, 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 6 gig stuff to do anything. It's just basically a controller. And those actually, like, remember the chips go to space is completely different from the chips in your phone or your monitor or your computers. Those are actually consumer electronics devices. The chips goes to space. It has have a special treatments. It has to be radiation hardened. It has to tolerate much larger temperature range, and those are very expensive to produce. Not expensive because actually it is because actually it's very low volume products. Okay, how many CPU you need? How many satellites you have, or like how many? Like this is actually hundreds, right? So that's like, for example, actually, if your iPhone, if you produce the iPhone, your iPhone, you buy it for $1,000. But if you produce from this iPhone only 10, each iPhone will be $1 billion, for example. Right?
Yeah.
Yeah. So those actually, so that's why it is the advancement in electronics in aerospace and or like satellites and stuff is not as consumers. Consumers actually, we can tip out actually chips every thousands of chips actually every year, right? Like you see all this like. But for aerospace, because the demand is low, people basically, someone has to spend the money basically to build these chips. So typically, like if something works, people recycling. Actually, is this board work for some missions? Let us use the same board because it has to go through qualification and stuff like that. So they have to share it between missions.
Okay. Are they coming up with another generation to replace Webb?
Absolutely. Actually, believe it or not, remember James Webb actually proposed in 1989, 1 year before Hubble, because Hubble actually has a lifetime of at this time actually was 10, 15, but Hubble was very lucky. Why? Because we have the what's called the space shuttle. So anything happened wrong with Hubble, send the space shuttles, astronauts actually will go outside and fix it or replace upgrades. So Hubble actually goes through like 3 or 4 upgrades. Okay, and so Hubble actually was able to survive for that long, but it's not basically there is no space shuttle anymore. This means that if something goes with Hubble, the next time we're gonna see Hubble as a ball of fires falling from the sky. Unfortunate. James Webb, because it is far away, it's never been designed to basically be maintained. Okay, so it has to basically survive by its own, and they just basically announced the starting point of as a successor of James Webb, because James Webb most probably actually it is designed for 5 years, but the engineers and scientists actually like the science space like they believe actually it is easy, they can extend it to 10 years, but there is some discussion that is okay, it even actually they can survive for another 15 years. It is just limited by what is called the amount of fuel, because actually you have to correct the locations. You remember actually it has to do this. So basically it has to fire to maintain its locations in the orbit. So they basically need to maintain a balance of how so basically they don't want to basically burn so much of this fuel, and they come out with new plans, okay, on people doing images, like they don't want to basically repointing back into some subject. If you miss your subject, you have to wait until 1 year until basically go back into the same subject. They don't want to basically move so by this strategy, they claim actually they can basically survive for 15 years. But it is proposed that a new 12 meter, this is a 6.5 meter telescope. They're basically planning 12.5 meter, a 12.5 meter telescope. And they basically claim actually it should be able to launch, I think actually 1935, something like that. Okay. And it turned out actually this is 100 years of the birth of what's they call it Sagjan, correct? And like it's basically like when they already starting to plan. I think actually they have to fund it. Means that is okay. They have to take, like, of course, like NASA is a federal agent, so it has to be approved, and someone has to basically sponsor, and because they have already money allocated to whatever missions active now. So if you want to plan another telescope, you have to basically find a fund for it, or basically have to delete some other programs. They have to manage that. But this is actually like, yeah, they basically started to talk about successor for Hubble, for James Webb, 12-meter telescopes. And the reason for that is, this is basically will be mainly for exoplanets, same size as Earth. You need a resolving power. It does not exist today in James Webb to do that, to see exactly the next Earth. You need much bigger telescopes and much better sensors than the whatever Webbs have today. James Webb, can do observations for planets that are far away from its stars, okay, and large, that is as large as Jupiter, or even much larger than Jupiter. But if you want to do an Earth-like, very close to sun, to the stars, its own stars, spectrometers and imaging, you will need much bigger telescope, plus much better technologies than whatever James Webb have today.
I was wondering, Hubble produced, I think, not just a deep field image, but also an ultra deep field.
Correct.
Is there going to be an ultra deep field image that Webb will be producing?
I think they don't have to basically call it ultra, like, because Webb is much faster and much bigger, because it's much bigger telescope, so doesn't need to go longer than, like, I think actually they conclude that is okay, like images actually in the range of 15 hours will be good enough, like less than a day is good enough for this ultra deep field images. So yeah.
I understand that, but
Yeah.
Is what you're saying implying that what we have now with the deep field image that is shown right now,
Correct.
is that the best that we're going to get?
Yeah, pretty much. Like I don't claim that, but actually you can basically this is by itself actually is a marvelous, amazing, impressive image. You get it in very short time, like what happened here. And of course, like some it depends actually what is like it was good enough for the science team basically to do all this research on it. And if they need more exposure for some specific items, like some of those items actually is very, of course, like the original image, you can download it from the internet. It's much more resolution. This is a cut and paste from like an image, okay, to screen. So if some science actually you want to have much more brightness from some subjects, you have to basically expose it more. There's nothing. Webb actually is capable to do that. It can basically track subjects, pinpoint to subject actually in for multiple days and even a weeks. So it can basically do ultra but it is not required. I think actually, like I have seen all the programs. I didn't see anything actually. Someone is asking more than few hours actually on the for using the a few hours from the telescope.
If I can interject a comment here, the Hubble Deep Field. May somebody turn off your microphone, please? The Hubble Deep Fields were made by simply staring at a blank piece of sky and to see what's there. This image from James Webb was not made like that. It's looking at a galaxy cluster and the gravitational lensing. The lensing not only creates those distortions, but it magnifies like a magnifying glass. It can magnify by a lot, like by 100 or 1,000. It has very powerful magnification. So not only do you have a 6-millimeter mirror, you got a magnifying glass in front of it that Hubble didn't have. And that's how you're able to see things that are so dim. And all the Hubble deep field images, and the ultra deep field was the last one it made staring. All the other ones after that, it made just adding images to it. That was all those deep field images were done on director's discretionary time, which means that the director of the telescope, since he's doing all the office work, gets free time on the telescope. He doesn't have to propose, do whatever he wants. And nobody would ever let you propose to stare at some empty piece of the sky and see what's there with a telescope. They just shoot you for putting in a proposal like that. But the director, he can do that if he wants to, and that's what he did. And it was so successful, they did a whole bunch more. I don't know how this one was made, if it was just director's discretionary time or not. But as our speaker said, it only took a few hours to stare at them because he's got a gravitational lensing. If you repeat the same kind of exercise the Hubble did, staring at some blank piece of sky, that will not be because somebody proposed to do it. It will be because somebody in the director's office or somebody important said, we're going to do this whether you like it or not.
Correct.
So this is
So,
probably deep as you get.
correct. Yeah, so those images was not basically part of the director discretionary. I think actually for the first 6 months there is no I didn't see in the plan any director discretionary. It's basically was actually like the highest priority is basically for the people design the instruments, like the teams actually design the instruments. This is having the highest priority, correct? They have a guaranteed time on the telescope. And of course, like there is some major programs, okay? And those major programs actually are submitting their proposals, submitting their time requirements for each team. There was no, like all these images until now was almost planned upfront, actually a few years, actually even few years ago. Remember, actually, James Webb actually delayed by almost 10 years. Okay, like to keep basically postponed the launch of James Webb for so many years. And so all this actually proposals was submitting long time ago. And basically was planned actually very long time ago. Like this time, 6 time slots are was scheduled a long time ago.
If they were to put up a telescope bigger than the James Webb telescope, would very much be gained by it, or is the James Webb telescope able to see back as far as there's anything to see, and you wouldn't gain much by having a bigger telescope?
Yeah, it's a good point. I think actually like a bigger telescopes will help. It's not gonna help much in this field, but also it could it depends actually what James Webb is gonna discover, because it is again it is early in the discovery. Remember, James Webb It's only 1 year, okay, less than a year in operations, correct? Yeah. So it depends on the discoveries, okay, of James Webb. Maybe actually yes, maybe no. But a larger telescope actually has a different actually will let us basically James Webb will play a role to identify, do spectrum analysis in some of the planets, okay, some of the planets around nearby large planets in nearby stars. The next generations, we know that as James Webb has its own limitations on resolving of those stars, right? Those planets, okay? A bigger, for sure, like we have to go, no matter what, we have to go bigger to basically resolving those planets, Earth-like planets closer to sun, to stars, because remember, actually, sun like us is rare in the galaxies. Like our sun is rare. Okay, most of the, like if in night sky, most of the stars, okay, will be much smaller than our sun, right? So if you want to basically look for planets, same for a stars like stars like our sun, plus actually has a planets similar size as Earth. So, like James Webb actually can look for those actually, but actually it has to be to resolve the resolving power has to, like those stars actually have to be very close to our solar system, right? Very close by. But if you want to basically, but those could be basically in tens or something like that, correct? And maybe you're not lucky. You do these observations. So if you want to go slightly further and look for Earth 2.0, you need much bigger telescopes than James Webb. So basically, like regardless, actually, how the deep field science, there is a lot of other science actually would depends on higher resolution telescope than James Webb.
I want to thank you for your
I
time
just
and
had
effort.
I just had one question. What other kind of stuff is James Webb looking at the moment?
So, like a typical day, okay, for James Webb, has multiple observations based on multiple programs. If you go to the internet, you can see that basically there is some new findings about like looking into the first spectrogram from analyzing the atmosphere of a planet. Okay, and I think actually this has come a week last week or something like that, correct? And basically, we discover there is some find a planet which has atmosphere, and it is basically has some they discover that it has CO2, it has methane, it has even it has silicate, correct? So like a typical they basically they have to basically prioritize the programs equally. So you see there is a lot of observations coming from exoplanet hunting. There is some observations about spectrums, okay, aging the accurate aging of our Milky Way, and there is some observations about the early universe. There is some observations actually about the star formations. Like some of the images you can see those about the star formations. So as I mentioned, like basically it depends on the program. It's like Hubble. You have to propose, okay, and people will agree what is the like if you accept your proposal, then you have to schedule you based on they have to schedule you, right? it depends actually what part of the sky you want to look at, like for your proposals, and you have to schedule your, like you are in October, this time, between this time and this time, you're gonna basically receive your images. So every day is not specific like to day-to-day operations, or like a week-to-week operations. Okay, it is pre-planned based on like they have to prioritize most of the programs. Okay, and there is, of course, like as I mentioned, there is some priority for the people actually work on the science of the gyms, like the science instruments. Okay, they have some priority, correct? And some of the programs that is they believe it can produce interesting science and low-hanging fruits. Basically, they can say, oh, for sure we're going to discover something by looking into that. Like, let us basically say, okay, James Webb discovered did analysis for ever, the first spectrum for the first exoplanet ever. Okay, something like that, correct? Those actually will take a priority, and basically they produce, like if you go to the internet and go and now actually I stopped actually to look into internet actually for generic article, because I see there's a lot of nonsense. But I typically go to NASA, or I go to the Space Telescope Science Institute. It's TCSL, something like that, for the latest and greatest informations. Yeah. If you need very high level, you go to NASA. If you need slightly detailed, you go to the Space Telescope Science Institute. And if you need much more details, as we today, you just go and read the like the scientific paper. And typically, those actually is not is hard to read, because you have to basically be from this team basically to understand what the guys actually talk about. But typically, like you can look into the summary, you can look into the process, but you don't have to dig in, because actually it's not like it's not your full-time job basically to understand every single word actually in this article in those scientific paper. But at least you can see the diagrams, you can see the summaries if you need that level of details. But between NASA website and the GIMS, the Space Telescope Science Institute, which basically operates James Webb, that is basically you don't need more than between these two.
Thank you.
Like, mhm.
All right. Okay.
Thank you.
Thank you.
I won't have to listen to that about 5 times.
Yeah, I actually like that. Yeah, it's basically it's this amazing program. I think actually is I think actually there is I think we are very close, okay, to answer very interesting questions, okay, about our universe, about our origins, about between the Large Hadron Colliders, between James Webb, between all these missions to collecting data from Perseverance, and between all this in Mars missions, okay, I think we are very close to answer very interesting questions. Hopefully in our lifetime, correct? Like we really alone, okay, like in this universe, and basically it is, you know how big is the universe. Like you see this image has like this is a grain of salt, a grain of sands in the tip of your mind. This is basically the field of view of this image, and it has 5,000 galaxies. Each galaxy has hundreds and billions of stars, correct? And each we know this is recently only, like in before 1980s, no one basically talked about planets after outside any star. And now actually this confirms thousands and thousands, tens of thousands of planets around stars. And we know now actually each star, most probably actually has planets, planet system, right? And those between James Webb and Carl Sagan telescope is the next one in 12 years, we should be able to identify something similar closer to Earth, and basically do spectrum analysis in the atmosphere and say, okay, there is a biosignatures in the atmospheres, and there is something's there. Okay, so that's basically the question. It took humans million years, okay, until we reach to this point, and we are lucky enough to basically to be in this era of this massive, huge discoveries. It will come from the LHC or something beyond the LHC, like Large Hadron Colliders in CERN, or Perseverance and beyond. Okay, and all these missions basically planned to go and discover the solar systems and discover the moons of Jupiter's and moon of Saturn's for life, actually. And this actually will, it could actually change our views actually about the universe, correct? Like, but we have to be careful before we declare victories, correct? So.
Yeah, okay.
Yeah, thank you. That was very interesting. I especially, I learned a lot from you about the camera that I did not know at all about before.
Oh, thank you. Yeah, I think I personally actually I was a design engineer for cameras, so I have you know
It shows.
so I can basically talk about some the sensors and cameras for hours and days. And basically, matter of fact, actually, I gave a talk to some organization, and basically, I only talk about the materials used in the sensor in this James Webb. The materials actually in little bit details, because actually the guys actually was specialized in the field of aerospace and stuff like that, and of course, like I have to, it depends on the crowds. I can go deeper or like so those actually was aerospace engineers, and of course like they have to endure me actually talking for like 1 hour talking about this the sensors material used in James Webb.
Yeah. I know there's been a proposal for the Hubble to reboost it.
No, people requesting now actually this Elon Musk to go and like either like retrieve Hubble or like fix it, because Hubble has redundancies. Okay, and if you follow Hubble closely, last year it lost one of its computer. It happened before, and when we have the space shuttle, we went and basically replaced the computer. But now we work with the backup computer is operating with a backup computer, and if the backup computer basically break, that's it for Hubble.
Yeah.
So but there is a proposal to send out another successor to Hubble, which is will be same size mirror. I think actually slightly larger. I think actually it is like two telescopes. They donated from some like military organizations to NASA, and they have to repurpose those telescope. Apparently, like those actually was not designed to focus on the sky. It's focused on something else. Focus on Earth or something, correct? So I think actually the now actually there is, because people love Hubble so much. Actually, it is like Hubble itself has more than 15,000 publication, and that's a lot actually. Like so people love. Still, scientists actually love Hubble, right? And still kicking in. Okay, but they know that is okay. If it break, actually, that's the end of it. So no one basically. So there is some talks actually, like try to convince someone like Elon Musk or SpaceX or something like that to go and basically have a special mission to basically either retrieve the shuttle or like the Hubble, or like to fix it if required.
Yeah.
But I don't think actually this is gonna go. I think actually they're gonna basically plan to launch those two telescopes I spoke which is similar structure architecture, similar to Hubble, and it is will let Hubble go if it breaks.
Yeah. Yeah. Okay.